So this talk is about, can others reproduce your conda results using pixi to manage dependencies in a Python data analysis project? There is a related talk that talks about using UV, and we'll just very briefly mention UV today, but there is a whole other talk as well, which is in the linked notes, which you can go to. The link to the actual talk material will hopefully be going into the chat now from Pau as well, but if not, I will share it at the end as well. So today we'll talk about what pixi is, and as I say, just talk briefly about UV. We'll try and give some motivations for why you might want to look at using pixi over conda. We'll talk about how you would go about configuring pixi for a standard project, and then we'll try and give some more context for what this means in terms of a data science project and what you might actually do. I like to just add a little note that I'm not the developer of these tools, so you may know more about them than me. You may have some advice. I'd be really happy to hear that. Any tips you have are welcome. And there's a couple of colleagues from the JGI, Leo and Rita, who I think are on this call, and they have been using pixi actively during one of their recent projects, and it's been really good to talk to them about how they use it. So yeah, thanks to them. Firstly, what does pixi do? Well, if you've used conda before, it allows you to install packages from conda repositories, so it's very similar in that way. However, it's also a bit like the tools UV and Poetry in terms of how it manages those environments. So rather than conda, where you install packages and then you manage your own list of dependencies, perhaps an environment YAML or a requirements file, pixi will do that bit for you, and it does this using what's called a lock file, which we'll talk more about. Pixi also has support for multiple platforms. Now, that's not just installing, it works across multiple platforms, but also it allows you to develop with the developers of a project on multiple platforms. And that's something that we're going to show that with conda can sometimes go wrong. And possibly the way it works, another example I put at the top there, NPM, that's the Node package manager, which is something from the JavaScript world for Node. It's perhaps a little bit more similar to that if that's something you've used before. One thing to add there in the way that what pixi does is, because it makes setting up a Python project really easy, and it follows some best practices, or modern best practices, I would say, for reproducibility. It's really good for bootstrapping, sort of setting up a project, let's say, when you're working with someone who's not so familiar with Python, and you don't have to bombard them with lots of other kind of environment-based commands, or you've got to run this, and you've got to activate this and run this. You can kind of simplify that step once pixi has been installed. And then even better than that, if you've got some tools that you like to run inside the Python ecosystem that normally you have to install inside environments or inside your project, but actually you want to use them globally across your system, you might have used tools before like pipx. Pixi supports something like this, so you can do pixi global to install tools globally, or pixi exec. It just lets you run things from conda packages without having to formally install them. You can define shortcuts for frequently run commands. These are called tasks. Pixi's got this built-in task runner. These are really useful for new users, where you want to just give them a simple command that they can run that might actually do something more complex. And we'll show an example of that in a bit. And you can also create multiple environments. And what I mean by that is slightly separate lists of packages. You might imagine that if you have a project, you have some core packages, some core dependencies that project needs, but it might also have some extra packages it uses for testing or for compiling documentation. And maybe some of these extra tools that you use are quite big packages or complicated things to set up. And what you can do is you can just have effectively a base environment that everyone installs, and then people only use these other dependencies for kind of more complicated things if they choose to. It's really easy to install. It's very fast when it runs, and I've found that it becomes more and more useful as a project grows. Just to look at a little bit of information about the project, it comes from the developers of Mamba, which is effectively a faster solver for conda environments that's now actually just built into most distributions of conda. So if you go and download conda from, say, Miniforge, that distribution, then you'll find that it has Mamba built into it. And the same developers as Pixi also released this tool, have released this tool called Micromamba, which is quite interesting. It's a single executable version of Mamba, but you can also just rename it to conda, and you can use it as if it's conda, but it's just one executable. It doesn't need a base environment. So it's quite good for using on things like HPC or continuous integration setups. As you can see from the graph there, first released in June 2023, and it's fairly actively developed, number of releases each month. And I found that most of the recent releases that have come have more been around speed improvements and reducing resource use just to effectively make the tool better. A comparison now with UV. So I've just picked out in red effectively the differences with UV. I said Pixi installed conda packages. I should have also said it can also install packages from PyPI as well. If you use UV is focused on PyPI packages. So if you don't have a need for conda, I'd really strongly advise you check out UV. Similar to Pixi, UV allows you to install the packages, but also the version of Python that you want to use. And so again, it's really good for bootstrapping new users. I'm going to talk about Pixi now for the remainder of this talk, but a lot of the concepts are very, very similar. And if you watch the other talk, you'll notice, there's some slightly different examples, but you'll notice how similar they are. So I promised you an example. I'm going to start with why properly managing dependencies is an important thing to do. And I'm going to show how with conda, you need to be careful when doing that. So this is where it gets scary and we switch to the live demo. Right, so I'm inside my system now. This is a skeleton system. I've got conda installed, but I haven't got Python installed yet. I'm going to just list the folder to see what's inside, so you can just have a look. We've got a myscript.py file and an environment YAML file. So I'm going to have a look at what's in the myscript.py and what's in the environment YAML. So I'm going to cat my script dot, spell it properly, myscript.py. This is, it was the simplest example I could come up for maybe something that you would want to do that's to do with statistics. So we import a function called binomial test from the scipy.stats package. And then effectively, we're assuming that we have this coin. We're going to flip it a number of times and we only see one head. And we're going to say, is that evidence that the coin is biased? So if you know anything about statistics, and I don't know a huge amount, so bear with me if I'm wrong, but we've done a binomial test here and we look at something called the p-value. And that gives us evidence for how unexpected, it tells us how unexpected the result was. And the smaller the number, the more unexpected that result was, the more it implies a coin is biased. So I'm going to look now at environment.yaml, look inside this file. This is, I call it a handcrafted file. So I've made this project myself, this file myself. I've said, I'm telling conda I wanted to create an environment called my_env. I wanted to use the packages from the conda_forge repository or conda_forge channel. And the dependencies I've specified here are some version of Python 3.10, just a single equals there. And then exactly version 1.21.6 of NumPy and 1.7.3 of SciPy. And that's the double equals sign here. These are quite old versions. So what I'm effectively simulating here is the project was created some time ago. Now, because I called that file environment.yaml, I can actually use a little bit of a shortcut built into conda to create the environment. I can just type conda n create. You can specify an environment file, but if you do it this way, conda will just assume that you've called it environment.yaml. So I can run that command now. Conda will download the updated repository data from online. It will think about it for a bit. There's usually a little bit of a delay here. It solves the environment, and now it downloads the packages that I've asked for. It installs them, which is what it's doing now. It's also telling me that there's an update available. And it finishes here with this handy line, just reminding me that I need to activate this environment in order to use it. And it's just repeated the name of the environment to me here, which is my_env. So I'm going to go and run that command now, conda activate my_env. Hopefully this is really familiar to people, but you'll see that the start of my prompt has changed. So we've got my_env there. I'm always a bit distrusting of whether this has actually worked. So I don't know if it's just me, but I always tend to type which Python. to see what the executable is for the version of Python that would run if I typed Python. If you're on Windows, where Python would be the equivalent kind of command. So I think, this looks like it's in MiniForge and in the myenv directory. So I'm pretty sure this is the right version of pandas that's going to run. And I can just check the version Python space -V, and that will tell me, yeah, as expected, I've got some version of 3.10, so 3.10.17. So now I've confirmed all of that, I'll go ahead and run my Python script. So Python my script.py, and I get some output. I get that the p-value is 0.021. Now, in a statistical sense, this means that, this is quite unexpected, flipping a fair coin 10 times and just getting one head. It implies that maybe the coin is biased. If you remember the 0.021, that's going to come up lots of times, so it should end up being quite familiar. In this example now, I'm going to think, well, what might be a natural progression? Well, potentially you might want to do some more analysis in your project, so you're going to perhaps install pandas. There's a number of ways of doing this. So I could go into that environment YAML file. I could add pandas as a line and update the environment from there. But a lot of people will just at the command line type conda install pandas. Fairly common thing to do. So conda will go away, solve an environment that has that version of pandas in. It's then come back and said, well, pandas version 2.2.2 will work with all of these other dependencies as well. Do you want to go and install those? Just hit enter, say yes. Okay, and that's completed. What I should really do now is I should note, having done it this way, that I've installed version 2.2.2. And then really I should go into my environment file, so nano environment.yaml. And at the end of this list of dependencies, I should really add in pandas 2.2.2, save, and exit to say, yeah, that's the version I'm using. But if you're working by yourself, you need to remember to do this. But if you're being really careful, that's probably fine. But at some point, you're going to probably forget to do that. So you're going to need to know, well, what are all the packages that I've got installed? So just to list what they are, we can just go on the list. We'll get a list of packages there. But it's worth noting that as well as the dependencies that we've asked for, so we asked for SciPy, I can see here, Python, NumPy, and pandas. We also have all of the other dependencies of those packages. And this is echoed by, if you type the commands to actually save, to update your environment YAML from all the packages that you've got installed, what most people would type would be conda n exports, and they'd say, I want you to save that directly into the environment.yaml, please. So similarly, let's go and look at that file now. So cat environment.yaml. We can see a very similar output here. So in our list of dependencies here, before we only had 3 or 4, we've now got lots and lots of dependencies. In addition to, say, the pandas 2.2.2 that we've added, we've got lots of other ones as well. So we can't see from here the packages that we actually desired and then the packages that effectively that we ended up getting. One of the ways that we can do this is we could type conda n export and supply the command line argument -- from history. And what conda will do now, it will only tell us the things that we've asked for. And somewhere hidden in your environment is a sort of a history file to say what things you went away and asked for. So you can see we've only got 4 packages here. But the thing to note is that we've only got pandas with no version number because we didn't actually ask for any particular version of pandas. So that command, this from history command, isn't actually very useful to kind of recover a reproducible environment.yaml here. So we should really export everything. We should really do this conda n for export. But we end up with this long list of packages like this with lots of these, as well as the version numbers, we've got these build specifiers afterwards. But that's really, I think, what we should do in order to make our environment reproducible. But at some point, we're working with somebody else. We're going to end up with them updating the environment YAML and then pushing that to version control and then giving that to us. And we're going to have to work with what they've given us. So let's assume that someone else makes updates to the project, re-exports the environment. But there's a slight catch. They're using a different platform from us. So back to my demo here, I'm going to just confirm that I'm using Linux and I'm using a 64-bit version of Linux here. Now, I'm going to assume, for argument's sake, that my colleague was using a Mac and they were using an Apple Silicon 64-bit version of a Mac. So I'm not going to use Git in this demo, but let's pretend that we pull some changes from Git. So I've just changed to a folder that contains that updated version of the environment YAML. And let's just list, and you can see we've still just got the environment YAML and my script. What I might do after pulling the changes that my colleague has made, I would type conda n update, and I can supply the handy argument --prune, which will remove any packages that I currently have installed that aren't specified in the environment YAML. So let's go ahead and run that. That will update all the repository data and try and solve. Now, might not be obvious what's happened here, but if I scroll up, we can see that it's looking for packages in the conda forge channel. I'm on Linux 64-bit, so that's what it's looking for. And then it tries to solve the environment and it fails. And the error message we get is packages not found error. The following packages are not available. And then we look down this list of packages, and it's slightly odd because NumPy, Python even, SciPy are in this list, but we think, well, surely those are packages. These versions are available. But if you're very eagle-eyed, you might notice in this list, in some of the build specifiers, you will see the architecture that my colleague has been using. So OS X ARM64. And even that is also encoded in some of these other build specifiers here, but it just doesn't explicitly say OS X ARM64. So remember, my colleague was running a Mac. That's why these have appeared. So I'm a bit stuck. How do I update my environment to match the versions of packages that my colleague has been using? Well, I could try effectively editing the environment YAML and actually removing all of these build specifiers that are in the environment YAML, which is quite tedious. I could make a script to sort of edit it automatically, but that might not even work, because what you'll find is there are some packages that are actually platform specific as well. So some packages only get installed on certain platforms. So it'd be quite tedious to go through and try and make this work. And certainly that's the experience that colleagues have had. And this is only 2 or 3 packages. So when you're working with a much bigger project, this problem just gets bigger and bigger. So how would this look if instead we're working with Pixi? So I've gone now to a fresh environment. I don't have Python installed, don't have conda installed. In fact, I don't have Pixi installed either. We're going to install it. So to install it, we would first go to the Pixi website, which is pixi.sh. The link's gone into the chat as well with that. We scroll down on the home page, and in the installation instructions, it gives us a command to run in a terminal, either Linux and macOS or on Windows. Now, the terminal I'm using is on Linux, so I would use this command here. But just a note before we run this command that you should usually be slightly suspicious of running commands directly copied and pasted from websites, because this will end up running code from the website directly on our system. Now, in this case, I trust the developers of Pixi. I've actually checked the install script as well, so I'm happy that I can go ahead and run it. So I'm going to paste that now into our shell, and then just before we run it, I'll explain what it will do. So it will use curl to download the install script, which is at this URL here, and then it pipes it into a new shell. So it will effectively run all the commands within this file, having downloaded it. So we'll run that now. We'll go ahead and download Pixi, and it's done. It's installed. It's installed it somewhere in our home directory. It also gives us a little message at the end to say that we need to restart our shell. We can do something called sourcing our configuration file. So I'm going to simulate now restarting our shell, and that will just give us access to the Pixi command. So let's pretend we restarted our shell, and we've now got Pixi available to us. So if I type the command Pixi, we get a little bit of help. We get all of the subcommands and a little bit of documentation for what they could be. There's obviously more documentation on the website. To start a new project, or workspace as Pixi calls it, I'm going to use the first command here, init. So I'm going to type pixi init. And what this will have done is it just created a configuration file using the toml syntax, which is a bit like an ini file, if you've come across that before, called pixi.toml. I can look inside the folder that I'm currently in. So I have my script.py, which was actually already there when we started. Pixi has now added pixi.toml, and it's created some extra Git configuration files with some sort of useful defaults in. I'm not going to look at those. I'm going to concentrate mainly on the pixi.toml here. Let's have a look at that. So cat pixi.toml. Right. What's in this file? There's a little bit of general metadata about my project or workspace first. So it says, similar to the environment YAML, I'm going to use conda forge. It says that the platform I'm working on is Linux 64-bit. And then it gives a name to the project, which by default is just the name of the directory I'm in. And it gives a version number, which actually doesn't really matter very much at the moment. And then there's some blank sections, which will automatically get filled up as we run some more commands. So the first command I'm going to run, a little bit like you would use conda install, I'm going to use pixi add, and I'm going to request Python some version of 3.10 as we had before. So Python add, sorry, pixi add Python equals 3.10. Pixi now says it's updating the lock file, downloading packages, and it's installed. And just to test that Python has been installed, the recommended way of doing this is forget about activating environments. This is the same kind of way if you've used UV that it tends to promote you doing things. Rather than doing the activate step and running Python, you prepend all of your commands with pixi run, and pixi will ensure that everything is effectively activated, that it's using the right environment and right version of Python. So you get very used to this. So I'm going to write pixi run Python -V, and we get back Python 3.10.17, which is the same version we got through conda. Now I'm going to add those other dependencies that we had before. So pixi add, and I remember it was NumPy version 1.21.6, and I asked for SciPy version 1.7.3. So again, the lock file gets updated, packages get downloaded. It's all done. Let's just try running the script first, and then we'll look at what's actually happened. So again, I would do pixi run Python, my script.py. So again, we're not activating, we're using pixi run. And we get the same script output with this 0.021 that we expected. So what's actually happened? Let's have a look at what's in this directory now. So we had the myscript.py. We had these Git files before. We have this newly created pixi.toml, which we'll take a look at what's happened. We have this pixi.lock, which is the lock file that it mentioned. And then we also have this .pixi, which is a directory, which we'll look inside in a second. But first, let's cat pixi.toml. Now, ever so slightly longer, effectively, all that's happened is when we type those add commands, pixi has gone in and filled in this dependency section of the file. So we've got Python 3.10 point something, and then we've got double equals exact requirements for NumPy and SciPy with those various versions. Let's look in the pixi.lock file, so cat pixi.lock. This is actually a YAML file, so it's another kind of markup language. And this shows all of the versions of the packages that have been installed. So this is equivalent to doing that conda env export line. So it says here for the conda forge channel, the Linux 64-bit, all of these packages installed. And you can kind of see the package names here. You can see kind of the version numbers come next. And then you can finally see these build specifiers that come right at the end. And this file is really, really long. So let's scroll down. Why? Because afterwards, as well as the URLs of the packages, we also get their cryptographic hashes. This is a way that pixi can ensure that the version of the package that you've downloaded is the version that was expected to try and make it more reproducible. And if I scroll all the way to the bottom, we'll find that this file is over 400 lines long already, only with a few packages installed. So it's not meant to be read by hand. What is meant to be read by hand, similar to conda list, I can type pixi list, and I can see a list of all the packages. So very much like with conda. Slight difference being you might not be able to see with the color scheme that I'm using, but the packages NumPy, Python, and SciPy are in ever so slightly a different color, might be bold on your system, and that shows that they were packages that I explicitly requested. Everything else is just a sub-dependency of those. If I just list those files again, if you're version controlling your project and you're not making a package, you've just got a project that you're doing some data analysis or something like that, then you should version control both the pixi.log and the pixi.toml file. You don't version control the .pixi directory, which contains it actually contains the virtual environment, also the conda environment that's been created. But you don't really need to worry about that, because if I look inside that folder, it's got this subdirectory called ends, which actually contains either all of your conda environments or links to them. But it has this git ignore file here, which is set to ignore the whole contents of this directory. So everything here will just be ignored and won't get version controlled. So now let's look at what happens when you, using Pixi, start to make changes to a project. And we're going to add some new dependencies like we did before with conda, and we're going to add a new developer who's on a different architecture like we did before with conda. So like before, let's say I want to add pandas. So I'd simply, there's basically one way of doing this. I would type pixi add pandas. I could also update the pixi.toml if I wanted. What does that command done other than downloading pandas? Well, if I look inside the pixi.toml, that's cat pixi.toml, you can see that pandas has been added here. And by default, what Pixi has done is it said, well, it needs to be at least the current version of pandas that's available, but not the next major release. So it has some rules that it uses to try and kind of enforce compatibility for you. And if you've got a project where you're doing a data analysis, this is probably a good thing to do. If you're writing your own package, you might have a different thing that you want to do, and you should probably do something slightly different. And we can check with Pixi list as well. So let's do that. And you can see, again, I've got pandas 2.2.2 installed. So that was installing a new dependency. What about working with new developers? Well, if you will recall that if I cat the pixi.toml, that inside this file, it listed the Linux 64-bit platform. And that's not the platform that the other developers of our project will be using. They're on Mac, or they could be, say, on Windows. So we need to edit this line of the file. But what I'm going to demonstrate is a way that you can do this using the Pixi command line interface. It's a little bit easier. It kind of checks that you've entered the things that are valid platforms. And I just type in Pixi to begin with. The command that I'm looking for in the list is a little bit far down here, is workspace, modify the workspace configuration file. So I'm going to go ahead and type pixi workspace. And then the subcommand I want here is platform. So I'm going to manage the workspace platforms. And I'm going to type pixi workspace platform. And rather than show you the help, I'm just going to tell you what I'm going to do. I'm going to add OS X ARM64 and Windows 64-bit. So that's and Mac using Apple Silicon 64-bit and Windows using Intel 64-bit. Pixi will now update the lock file using those two extra platforms. And what it will try and do is ensure that it has dependencies that are compatible across all of those three platforms. You can see the changes to the pixi.toml and the pixi.lock file. So in the pixi.toml, literally all that has happened is those extra platforms have been added here. This is something you only need to do once. And then inside the pixi.lock file, so that's cat pixi.lock, starts off looking the same. So we've got packages for Linux 64-bit. But if I scroll down, you'll see a new section for OS X ARM64, which is the Apple Silicon. And you'll see a new section as well for Windows 64-bit. So it's trying to list compatible packages for all of those different architectures. And then again, afterwards, we still get all of the hashes. And if we go right down, it's now even longer, and it's over 1,200 lines long. And a handy tool that you can use to see why you've got various dependencies installed, if you type pixi tree, you get back a little ASCII art printed tree that says, well, these are your dependencies that you asked for. So you asked for SciPy version 1.7.3, or that's what you have. And then SciPy has its own dependencies. So it has, say, libblast, libcblast. And then libblast, in this case, has all of these other sub-dependencies as well. So it's quite good for seeing why you're using a particular package. And if I scroll down, we can also see NumPy on this list. That's actually saying that SciPy depends on NumPy. If I keep scrolling down, you can see here I've got pandas as well, and then pandas depends on NumPy. So you can see all of the kind of interdependencies of things there. You can also list the tree the other way, and you can say, right, why have I got this package? Tell me what depends on it. So that's possible as well. So that's all very well and good, but what I've shown so far is a little bit simplistic. The thing I'd like to show now is, well, what does this mean in a data science context? So for an actual data science project, how might you use pixi? I'm going to switch now to another project that I've started. I started this project ever so slightly differently. I started this project rather than with pixi init. I've specified it with pixi init -- format PyProject. And what that tells pixi to do is, instead of using the pixi.toml configuration file, it uses a configuration file called pyproject.toml. Now, if you've used other Python-based tools, this might be it's a standard configuration file. It might be something you've seen before. If you've used UV, this is the same kind of configuration file that UV uses. I can show you what the project looks like. Oh, I should say as well that I already installed everything just to speed up the demo a bit. So you'll see things happen a bit quicker in a bit. This is what the structure of my project looks like. So I've got the pyproject.toml, which is the configuration. I have the lock file still, pixi.lock. And then inside a source and then my project subdirectory, I've got my script, probability.py, which we'll take a look at in a second. And I've also got a Jupyter notebook inside their notebooks subdirectory as well. So we'll look at everything in turn. We'll start with the pyproject.toml. So cat pyproject.toml. This is a little bit longer than the previous demo that we saw, and I've also customized. I've added a few bits to show off what you can do in the project. So what I've done is I've put some comments in just to help us understand what's going on in this file. We start with all the metadata about the project. So we have similarly this project section here, which, like before, has name, version. We've also got a description and author's information here, which you can obviously change. Then we specify the minimum version of Python that the project requires. So in this case, 3.11, but you could be more specific if you wanted. And then the following array or section here is for the PyPI dependencies. So these are the ones that effectively you would normally install through pip. If you wanted to add anything to here, the line to run at the command line is pixi add, but then -- PyPI, followed by the name of the PyPI rather than the conda package. For all the remaining sections in here, you'll notice they start with the words tool.pixi. This is to tell other Python-based tools that this is a pixi-based configuration, so they don't conflict with all their configuration sections. This is where pixi is saving its channels and the platforms information that we've seen previously. Underneath, we've then got a section called tool.pixi.dependencies, and this is the thing that lists the conda package dependencies. So these are the similar, slightly updated now, but similar dependencies that you've seen before. And I've also added this dependency called typer, which will provide us with a nice command line interface, which I'll show off in a second. If I scroll down in this file, the next section here is slightly confusing, but what this does is it makes the source code of our project available as a package. This is very useful if we're running scripts or running Jupyter notebooks, because we can put all of our functions and things like that into separate package files, and they will be importable from wherever we are, whichever notebook we're in, whichever script file we're in. So if we use these two sections here, which get created by default for us, then we don't need to worry about sort of changing the Python path, making sure that the library file is in the same file, same directory as our notebook or our script. So we'll see that later as well. Next, I show off how you install those non-essential dependencies. So this is using that thing called multiple environments that I spoke about. First, in this section, we create some features. So I'm showing you the commands that you would type there. But just to explain what's going on, I created a feature called Notebooks that uses the conda package Jupyter, and it doesn't care about the version, just any version. And that's to give us Jupyter notebooks if we want them. And then there's another feature called Code Quality, which installs the packages rough and pylint, which are source code checkers and formatters and things like that. To bring those two features together, I've now, in this section, created an environment that uses those two features. So again, we've got the command there, but in summary, there's a new environment that we've created called deb, and it uses the notebook feature and the code quality feature. And then finally, at the end, I spoke about shortcuts or tasks. This is the task runner that Pixi has. So we've specified a shortcut or a task here called probability. And if we run that, it runs this command for us. So in this example, we're just running something from the project folder, source folder, called probability.py, that module. And then I've also created some more tasks that are specific to the various features. So this is the tasks for the notebook feature. There's a shortcut called lab, which will just run Jupyter Lab. And in code quality, there's a shortcut called format, which will run rough format over the source directory. So you can think of lots of common things that you might want a developer on your project, perhaps yourself, to do. We've looked at pyproject.toml. Let's now have a look at the probability.py file. So at source my project probability.py. You'll recognize that this bit of the source code is that similar p-value bit before. But what I've done is I've wrapped that up inside a function called testCoin. And I've specified arguments. So rather than hard coding 10 flips and one head, I've said times flipped and heads observed are the arguments that are then used lower down. And for the purposes of this example, I've also put a test dice function as well to show kind of a similar functionality in a different context. And the key difference here is at the top, I've created this app object from the typer library here. And then I've decorated these functions with app.command. And we'll see what happens in a second when I've done this. Right at the very bottom, I just say, if you're executing this file directly, then call the app object. So what effect does this have? Well, let's look at tasks. If I type pixi run, we'll get a nice list of all the tasks. Now, I could run pixi run Python something directly, or I can run one of these the tasks that I've defined. So I'll start with pixi run probability, which, if you recall, that was the shortcut to run that probability.py file. And because I'm using typer, I should get some nice help that tells me these are the commands that you could run. And they are those functions that I've decorated. But you'll just notice they're not separated by underscores. All the underscores get changed into hyphens. So I can run, let's say, pixi run probability test-coin, and that will run the test-coin function. So we've created very easily a command line interface to our library. And if I run that again with --help at the end, you'll see that it tells us the different options that we can supply, what type they need to be, and what the default is. So that's all picked up from the function definition for you. And in fact, if there was documentation, that would get added here as well. So you can imagine running something like pixi run probability test-coin -- times flips. The default was 10, let's say 20. And we flipped the coin 20 times. P-value is very, very small. So this would be very, very unusual, definite evidence that the coin is biased. Right, so let's take a look at the notebook that I put inside the project folder here. So I'm going to, I'll type pixi run just to look at those tasks again. I'm going to run the lab task, which just runs Jupyter Lab for me, but it's just a bit shorter this way. So pixi run lab. So that will go ahead and run Jupyter Lab for me. And if I click the right link, load. There we go. Phew, almost got it wrong. Right, here's the project that I've got. Let's look inside notebooks. Here's that example notebook, which we'll have a look at. And then I'll also open the source, my project probability.py file next to it. Let's get rid of that to give us a bit more room. Right, so what's going on here? Let's just look at the notebook for a second. Well, from the my project package, from the my project library, I import the probability package, which is this file on the right-hand side here. Notice I don't have to do anything with paths. These are actually completely separate directories, but if I run that cell, it will work correctly and everything will sort of magically work, which is really helpful. Makes our notebooks really tidy. Then there's a little bit of magic that I tend to do whenever I import from my own project, is I run these two lines here, which make use of a Jupyter auto reloading trick that mean that if ever I make changes inside a source code file here and save it, it will automatically get reloaded inside our notebook kernel. And I don't need to worry about restarting the kernel ever. So let's run that here. And then we can run this test coin function that we've got on the right-hand side. Okay, and we get the output that we expect with the 0.021. Just to demonstrate this auto reloading, let's go in and maybe just put some asterisks in or something like that, just to demonstrate changing the output. And we'll save that file. We'll go back to the left-hand side. The only cell I'm going to rerun is this one. You'll see that the output's automatically changed for us. So this method of having our main source code inside a library file or a whole set of library files, keeping our notebook clean, is really something that we try and recommend that people do. And it's really nice that Pixi actually makes this really easy for us. Right, so I'm going to go through just another couple of tips quickly for working with Pixi. So I'm going to close the Jupyter server down. One of the things I mentioned earlier was how you can install global tools so that they're accessible across your whole system. So I'm going to look at two ways of doing that now. First, I'm going to try installing Quarto, which is a tool used to compile notebooks into web pages and other like PDF and other outputs. It's really, really useful, works with Python and R. Thoroughly recommended. It's what these slides are made in. I mentioned Pixi Global before, so I can start with Pixi Global, and all I need to type is Pixi Global install Quarto. Quarto is a conda package in this case. If I run this, Pixi will then go off. It will create an environment for Quarto that's separate from all my other environments on my computer. It will install Quarto into that environment, and then it will make the Quarto command accessible to my shell without having to activate it. I could be anywhere. So we'll run that line now. Download and install Quarto into that environment for me. And then it tells me, right, so these commands are now available anywhere on your system where you've got access to Pixi. So I can type now just Quarto. I make Quarto help. Didn't have Quarto installed. Now I have Quarto installed. So it's really easy, and that's all you need to do. And you have access to all the packages in the conda ecosystem if you do this. There's a similar command if you're using UV. It's UV tool, not UV global, but very, very similar. Another example, perhaps I don't want to install a tool permanently, but I just want to try one out. I've heard of this tool called Rough, which I mentioned a second ago, but let's pretend we don't have it installed. And I want to say, oh, maybe Rough is a tool that I might want to use. I know it's a conda package. I can actually just type pixi exec Rough. That will do exactly the same thing as global install, but it will do it in effectively a temporary environment. So I run pixi exec Rough, and I haven't run any arguments, so I just get the help for Rough. You noticed it downloaded and installed Rough. To run it again, so I can't type Rough because I haven't installed it, but I can again just do pixi exec Rough. And you'll notice, hopefully this time, maybe it gets checked for updates, but it's much faster because it's cached. Right, so wrapping up, I would strongly encourage that if you're interested, that you find out more about these projects, either Pixi or UV from their websites. I would suggest, this is my personal thoughts, that actually Pixi, if you're using Conda, or UV if you're just using PyPI, I would recommend that you use them for new projects. If only the sort of two of the things that I've shown today, that source layout where you have a package inside a source directory or subdirectory inside source, that's really convenient. And both of these tools set that up automatically for you. Also having these tools that you can run, like Pixi Run. Imagine having a person that you're working with, and that maybe in your README file, you just say, to run the analysis, run Pixi Run analysis. Then that's kind of really quite powerful in terms of simplifying your documentation. What the commands are still all in version control in that Pixi TOML. If you're working with someone who's new to Python, I mean, the sort of temptation is to just use pip and conda, the sort of standard commands. But what I would want you to take away and consider is, let's say you give someone some source code somehow, and you make sure they've got Pixi installed. Let's say your project runs a dashboard for them. The only thing you would need to tell them to do is to run Pixi run dashboard at their command line, and that might be the only command they need to actually run. And I think that's quite powerful. That will, as long as the project source code is up to date, that will make sure that they've got the correct versions of everything installed and manage all their environments for them. So finally, I hope I've demonstrated that, doing it this way is going to be easier in the long run than using conda or pip by themselves. And one of the things that I sort of make available, the demonstration little mini projects that I set up here, on the online materials that will be linked to, that you can just go and look at what those are. And if you want to use those as kind of inspiration for your own project, then please do.